Welcome back to Secret Weapons for Game Design. And now, a case study, AI and Digital Games. At their talk earlier this year at the 2020 DICE conference, Google Stadia Creative Director Julian Cuny and Vijay Sundaram of Google Research illuminated a few opportunities for how to integrate AI into game design to add value, excitement, and accessibility to the player experience. Let's take a listen.
When you think about the relationship between AI and games, you might think of something like this. AlphaGo beating Lee Sedol at Go. Or this, Watson beating reigning champions at Jeopardy. Or this, Deep Blue beating Garry Kasparov at chess. In a sad sort of way, these moments seem to define the evolution of modern AI. Research has gotten really good at using games to advance AI techniques and beat the crap out of humans at their own games. We're trying to flip the relationship between AI and games, so it feels a bit more like this. One of the areas we're really excited about here is reinforcement learning. It's an approach for computers to learn what to do or how to act based on trial and error and feedback through rewards. For a gaming analogy, it's like dropping an unprogrammed NPC into a game and have it learn to figure out how to play based on mashing buttons and tracking its score. To make the analogy between these worlds a bit more explicit, in gaming, a player uses controls in a game that results in changes to game state as well as scores that the player can then see. In reinforcement learning, an agent takes actions in an environment that result in changes in that environment, as well as rewards that the agent can observe. Now, researchers experiment and they tinker with different parts of the system. Designs for the agent and the environments, actions and observation spaces, reward functions, to train agents to do all kinds of things. And so you think this might be the kind of thing they're looking at all day long. But there's also a whole lot of this. What you're looking at are the results of reinforcement learning. Agents that have learned policies to maximize rewards in the specific environments and tasks they were trained on. Sometimes these agents amaze us. Here you see an agent that's learned to both kick a target and to do it in a very specific kick style that was shown to it. And it's learned to do those simultaneously and cope well even when researchers peg it with boxes and be mean to it. Some of these agents surprise us. Here, in a boat racing game, an agent controlling the boat figures out it can score higher scores just by looping in circles and re-hitting targets that are spawning, as opposed to competing in the race at all. Some of these agents just want a derp. Here, this humanoid was rewarded to learn how to walk on its 2 feet just by being rewarded to go as far and as fast as it can before falling over. This has nothing to do with reinforcement learning, but it felt right here. What comes up over and over again as we're going through these examples in our own experiences is that they're surprisingly entertaining, which got us thinking, why do researchers get to have all the fun? In maybe an overly romantic way, you could look at their work as a form of play and tinkering filled with joyful wins and surprises, epic fails at what these agents learn and do. It's just that this process is kind of intense and inaccessible to the rest of us. But what if we can make this same process fun and accessible without losing the magic of reinforcement learning? Players could define goals and rewards for agents or show demonstrations to help them out, or give feedback through things like cheers and boos. We need these interactions to feel great for the player, not just work technically, but if we can pull it off, these could become new mechanics that give players a form of expressivity they haven't had before, through the form of character behaviors. Now, one idea we're exploring is how a new machine learning building block, generative models, could help supercharge things. Think of a generative model as a function that can output newly generated examples that feel like part of the data set it was trained on. You can contrast this to other machine learning models that predict things like chances of rain or classify things like cat versus dog. The examples you see here were all generated by state-of-the-art generative models trained on large data sets of faces. Each year represents the state-of-the-art results for that year. Over just a few years, there's been rapid improvements to both the resolution and also the diversity of images these models can generate. So let's bring this back to artist tools and see how generative models could fit into the picture. What you see here is a demo from NVIDIA. On the left, a user sketches a layout for a landscape, and on the right, a generative model produces a photoreal rendering of that layout. Now, in this case, the generative model was trained on a data set of photorealistic landscapes, so it could produce a new one based on the user's input.
Looking at this slide, I know some of you are maybe rolling their eyes, but we don't. We think these devices have brought millions of new people to gaming, and that's extremely valuable to our industry.
So the Kinect and the Wii are really inspirational for us, especially given what we're trying to do with this entire collaboration. They created the category of motion gaming. And even though it's been a decade, the core of what made these experiences so special really hasn't changed. Moving still feels really good. It's still good for you, and it's still fun to do together. And these things are just as likely to be true a decade from now as they are today. But here's what has changed in the last 10 years. Computer vision, the ability for computers to understand content of digital images, like from an RGB camera, has gotten way better. You can see here how error rates on a standard recognition task have dropped to below 5% in just the last decade. Let me share a few more examples of work from Google that's particularly relevant here. We've gone from being able to tell if there's a person or not a person in a picture to now being able to detect skeletal structure, which pixels belong to which body part, for multiple people in a scene. We're starting to understand the activities that people might be doing in that scene. Here on the left, you see 4 different examples of a squat. Different lighting conditions, different camera angles. On the right, you see a visualization of how one vision model can understand all 4 of these motions are similar in their up and down motion. One simple use case for this is automatically counting reps. And again, without any accessories, just an RGB camera. Hands. We can now track hands and fingers at an incredible fidelity. And this sets us up to do higher level gesture understanding, like sign language, which is actually a really nice example of how to open up new interactions and accessibility for players in games.